You may have seen this pendulum and this spring mass system at class. You may also have been taught the periods of each one of them, all under the name of something called the simple harmonic motion. And they say blah 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 sinusoidal. But why? Why are they sinusoidal? Why is simple harmonic motion important? In this video, I will derive simple harmonic motion from ground up and mathematically prove why they are very common in physics. I think this video will be a great starting point for enabling you to solve challenging problems involving oscillations. Just to warn you, the second half of the video will require you to know high school calculus. So let's get started. In physics, we study the movements of particles under various forces, but we can also study objects that are not moving or objects that are stable. To see why this box is not moving, we have to study the forces acting on this box. We have gravity pulling it downward, and the normal force, maybe from the surface of the table, pushing it upwards. So, for this body to be in mechanical equilibrium, or stable, the total force of this body has to be equal to 0. Otherwise, obviously this body is going to accelerate and start moving. That means the gravity and the normal forces should eliminate each other. Now, imagine changing the shape of the surface and the body without changing the forces. We still have the same weight pulling the body down and the same amount of normal force pushing it upward. And according to our mechanical equilibrium equations, the forces are still eliminating each other, so they are still in equilibrium. But right now, your intuition must be screaming that this cannot be stable. And you're right, it's not stable. So, there are 3 different types of equilibrium. To show what I mean, let's create a curve and place 3 spheres at different equilibrium positions. Each one of them are already in mechanical equilibrium. Now, let's try moving these spheres just a little bit from the equilibrium positions. We have the 2 forces acting on the sphere, gravity and the normal force. The important thing is, if you add those 2 forces up, then total net force is in a direction that is away from the center of equilibrium. Now let's see what happens to the second sphere when you displace it a little bit. The 2 forces haven't really changed actually, and the total sum of force is actually equal to 0. Now, what happens to our last sphere when you displace it a little bit? The 2 forces, the weight and the normal forces, add up, and the net force will be pointing towards the center of equilibrium. So, the first sphere is unstable because just a little bit of disturbance is enough to create a force that pushes it away from the center of equilibrium. The second sphere is known as to be in a neutral equilibrium because when you move it a little bit, there's no force pushing or pulling it to the original location. The third sphere is known to be in a stable equilibrium because whenever you displace it a bit, there will be a force that pulls it towards the center of equilibrium. So, it can basically error correct itself. And that force is called as the restoring force, as it always tries to restore the equilibrium. And today, we'll be studying the stable equilibrium in depth, since it gives rise to oscillations. Now let's say we have a tiny ball inside a bottom of a ball, and it's moving without any loss of energy. We can visualize the restoring force in red. Note that this force is just a total force that the ball is experiencing. And let's plot the displacement of the ball with respect to time. The curve might look very similar to you. And this is indeed almost sinusoidal. I'm saying almost because of few reasons, one of them being that the bottom of the ball is curved, therefore the measurement of displacement is not clearly defined here. So first, let's talk about the condition on the restoring force that causes the movement to be sinusoidal or simple harmonic motion. Secondly, let's talk about why this condition is actually quite common, making the simple harmonic motion commonplace in physics. I mean, they wouldn't go through the trouble of making this part of a physics curriculum if simple harmonic motion was a very narrow concept that doesn't apply to many places, right? So, a simple harmonic motion occurs when the restoring force is directly proportional to the displacement. Now, let's take a look at the perfect example, the spring mass system, and prove that its movement will be sinusoidal. Let's indicate the equilibrium position and give it some initial displacement to see how it moves. We can visualize the force by using a red arrow. You may notice that the force is always pointing towards the center of equilibrium. Let's pause here and take a look. Let's indicate the restoring force and the displacement vectors. Let's use Hooke's law. Let's substitute the force by mass times acceleration. Acceleration is the second order derivative of displacement. And since the problem is one-dimensional, we don't have to worry about the directions of the vectors. Let's rearrange and divide everything by the mass. Now, this is the most important differential equation for simple harmonic motion. And you can safely assume that whenever you have an equation in this shape, it is going to be a simple harmonic motion. So, let's show that using mathematics. For starters, the k/m is just a constant that depends on the spring constant and the mass of the object. So, in general, we can write down the following differential equation with a positive constant, c. Instead of c, let us use another constant, omega square. And I promise that it's going to make sense soon. So, this equation has a solution as x equals a sine omega t plus phi naught, a sinusoidal function. I think solving the differential equation to obtain that result would be too mathematically intensive for the purpose of this video. So instead, I'll just show you that the solution would satisfy the differential equation. Let's start by finding the second order derivative of the solution. We can use the chain rule to find the first order derivative. And we could do the same again to obtain the second order derivative. And let's simplify the equation. Now let's plug the second order derivative and x into the initial differential equation we got. And we can easily see that they eliminate each other. We've just seen that the solution to the differential equation is actually a general sinusoidal function. Now let us find the specific solution to our spring mass system by comparing it to the general solution. And we see that k/m is the omega square. So, omega squared equals k/m, and the omega equals square root of k/m. I think you're already probably familiar with what omega is. But to the ones who don't know, it's the angular frequency of our oscillation. Now, you may also wonder how to find A and phi naught. To find those constants, we have to know the initial conditions of our system. How far was the spring pulled, and what was the initial velocity of our object? That will be specific to the problem. Okay, so we have just demonstrated that the spring mass system or any system with a restoring force that is directly proportional to the displacement oscillates in a sinusoidal pattern. But isn't that too specific? Let's take a look at the most iconic thing that is used to demonstrate the simple harmonic motion, the pendulum. In reality, the restoring force of the pendulum is not directly proportional to the displacement, but the pendulum moves almost sinusoidally, especially at smaller amplitudes. This is because, to achieve approximately simple harmonic motion, all you need is to satisfy following two conditions. First, the amplitude or the displacement has to be small. Second, the restoring force should be able to be expressed using a potential energy. The second condition is usually achieved when there is no friction or damping forces. These two conditions are much more common compared to the prior condition of having the restoring force that is directly proportional to the displacement. Let us summon the spring mass system once again and plot its potential energy. The potential energy graph is a parabola which is expressed as kx squared over 2. But what about other systems? In general, other systems would have their own potential energy curves, and the oscillations happen around a stable point. In other words, the minimum potential energy point. For convenience, let's shift the potential energy curve such that the minimum potential energy is at x equals 0. Now, let us approximate the potential energy around x equals 0 using Taylor-Maclaurin series. For starters, the first derivative of the potential energy evaluated at the minimum point is equal to 0, since the slope of the graph is equal to 0. We know that the force is equal to negative of first order derivative of the potential energy. So let us differentiate the potential energy to obtain the force. The derivative of the first term is equal to 0 because it's just a constant. And the second term is equal to 0 since the first order derivative is 0 at that point. The third term would be minus the second order derivative of the potential evaluated at 0 times x. And the remaining higher order terms can be written as O of x. When our first condition is satisfied, in other words, x is small, O of x becomes negligibly small. Therefore, we can see that the force can be approximated as minus second order derivative of v evaluated at 0 times x. Here, the second order derivative is already evaluated at 0, meaning it's just a constant now. So we can say it's k. And this should really remind you of something. Doesn't it look like the Hooke's law? So, it's almost just like a spring mass system. That means the oscillation around the minimum point is going to be approximately sinusoidal or simple harmonic motion. Finally, let's take a look at what it means on the potential energy graph. It means we just approximated the potential energy using the first 3 terms of the Taylor series expansion. And it will look like this parabola. We can see that the parabola fits our function quite well, especially at around x equals 0. Now this proves that any oscillation in a potential field when the amplitude is small will oscillate just like a simple harmonic motion. I hope you enjoyed learning about simple harmonic motions with me. Next time, I'm thinking about showing you how to solve some Olympiad level oscillation problems. If you like this video, like. If you want to watch similar content, please subscribe. Also, let me know in the comments down below how you find the level of difficulty of this video, and see you guys next time.